So, electrostatic equilibrium problems. Remember when we had a charge that was in the middle between two charges that were equal? It was in electrostatic equilibrium because the two forces applied to it were equal and opposite. So therefore there was no net force. That is what electrostatic equilibrium means. Means the electric forces applied to the charge keep it in place and it's not pulled either way any stronger than the other way. In our case, in this particular case, we have a charge number 3 that needs to be placed somewhere between the 4 nanocoulombs and 9 nanocoulombs. And just for the sake of the exercise right now, we're going to look at the charge that is positive, and it's just 1 coulomb. So if it's positive, it's going to be repelled. It will be repelled by 9 and by 4 as well. If I put it right in the middle between them, the 9 is going to repel it more than the 4. Because 9 is stronger. So that's not going to work. And in order for the forces to be equal to each other, I will need to probably get it a little closer to 4. So even though 4 is less than 9, because it's closer to it, so I'm going to say this is force from 4, and then this is force from 9. And the idea is to place the third charge, this is our Q3, somewhere that the two forces, the force from 4 and the force from 9, are equal. In that case, it will be, Q3, will be in electrostatic equilibrium. What we're looking for is the distance. I know the total distance, which is 0.4 meters. So what I'm going to do, I'm going to say this right here is x. This distance will be 0.4 minus x. And then we're going to use the formula for Q1, Q2, that's the general formula, over r squared. What we are dealing with is two forces, and they need to be equal and opposite. So I'm just going to write Kc times 4 nanocoulombs times 1 coulomb over x squared should be equal to Kc 9 nanocoulombs times 1 coulomb over 0.4 minus x also squared. Now see what we can get rid of. Kc and Kc. 1 coulomb and 1 coulomb. Both of these are nanos, so I can just get the nanos out. So what I end up with is 4 over x squared should be equal to 9 over 0.4 minus x squared. Problem is, if I were to apply the square, that would be a lot of work. If you notice, both 4 and 9 are perfect squares. Ba-bam, ba-bam. That becomes 2 over x, and this becomes 3 over 0.4 minus x. Well, from here, that's just pure basic algebra. It's going to be 0.8, I cross-multiplied, minus 2x. Should be equal to 3x. This goes to the right as a positive, so 0.8 should be equal to 5x altogether, from where x is going to be 0.8 over 5. That should be 0.16. If I were to use this, I should have 0.24 squared. It's the same! Now, question B for this exercise has, I believe, a negative, where it might have printed as a positive, but it should be negative. So, should we put a negative charge instead of a positive charge? Would anything change? Nope, it would not. And that is because if I put a negative charge, it's going to be equally attracted, and it will be more attracted to 9 if we put it in the middle, so we have to move it a little closer to 4, so the attraction would be equal. Nothing will change. The third charge does not matter. What does change things, however, is when we have a positive and a negative charge. So just for the purpose of the exercise, let me make this negative. And mind you, we're talking about the line that connects the two charges. Somewhere along this line, we're trying to figure out where to place the third charge on the line that connects these two existing charges, so that it would be in electrostatic equilibrium. I cannot put it in the middle because look at this. If I put a negative charge in the middle, it's going to be attracted to the positive charge and it's going to be repelled by the negative charge. Those forces are never going to cancel each other. I cannot put it in the middle. I can put it either over here where it will be repelled by 25, which is negative, and it will be attracted to 16. However, look at this. 25 is greater than 16. I cannot be closer to it because it's already greater. So what we need to do, we need to put our third charge over here. And again, if it's a positive charge, 16 is going to repel it, 25 is going to attract it. If it is a negative charge, again, the 25 is now going to repel it, and 16 is going to be attracting it. It is possible to reach electrostatic equilibrium. We just need to make sure that we're closer to the smaller charge and we are outside. So then I'm going to call this X and write again, Kc is going to cancel, but just for the sake of the exercise, Kc, then I have 16 nanocoulombs times 1 over x squared should be equal to, again, Kc, and now this is going to be, and it's absolute value, so I'm not going to bother with the minus, 25, again, nanocoulombs times 1, and in this case, this is 0.4 plus x, and all of that is squared. Let's get rid of dead weight of Kc, of nanos and 1, and we end up with 16 over x squared equals 25 over 0.4 plus x squared. And what do you know? We can root. Cross multiply. 1.6 plus 4x equals 5x. That's even easier. That just goes over here. And we end up with x equals 1.6. 16 to 1.6 squared should be equal to 25 to, if this is 0.4 and that's 1.6, that's going to be 2. So it's going to be over 4. Again, grab your calculators. They are indeed the same. That is how you figure out the place of electrostatic equilibrium.